Hi everyone, this is Dr. Barbara Sirotnik, and I have a short video here that will help you learn a little bit about linear regression. We're going to talk a bit about the theory, we're going to do some examples of linear regression, and we'll touch on multiple regression. So let's start off just by saying what is linear regression. And as you can see on the screen, regression is basically just prediction, or another word of forecasting. And this is where the variable to be predicted is quantitative. So some examples that you might think about would be predicting test score based on how much time you study, or predicting demand of an item based on how much it costs, or predicting the price based on the quality of a product. So that's what I mean by predicting one variable based on another. Now, I need to give you some definitions of independent and dependent variables. The dependent variable is the variable that you want to predict, and we call that the y variable. The independent variable is the variable that you're going to be using to do the predicting, the x variable. And keep in mind that the x variable can be either quantitative or qualitative, but for this particular procedure, the y has to be quantitative. There's going to be some other techniques we'll talk about later where the y would be qualitative. So here's the basic process that I tend to use. It's a two-step process. First, I look to see, is there a linear relationship between the two variables? And the way I determine that is by looking at a graph called a scatter diagram, and I look at statistics such as the correlation coefficient and coefficient of determination and some other things to see if they are related. And if they are, then I can continue to step number 2, which is the predicting. If they're not related, then I stop and go do something else. But step 2, I will find a regression line that will allow me to predict y based on x. And this actually looks sort of like the line that you learned about in high school, y equal ax plus b or whatever. And this is where in this case, the b0 is the y-intercept and the b1 is the slope. So let's start by doing a little review of something that you've already learned about. Is there a linear relationship? So just reminding you, if we happen to have data that goes from bottom left to top right, meaning as x goes up, so does the y, that would be a perfect positive correlation, r equals 1. In real life, you don't find that. You'll find a spread of points, as you can see here. So in real life, the correlation will never be 1. Some examples: the more time you study, the higher your exam score will be. Subtle hint, what can I tell you? Of course, not everything is a positive correlation. We could have negative correlation, and that means as x goes up, y goes down. Again, if the points are perfectly on a line, the r is going to be -1, but that never really happens. In real life, there'll be a spread of points that look kind of like this. Examples: the more time you study, the less sleep you might get. You kind of get the idea. As the price goes up, demand goes down, if we're talking about products. Finally, let's take a look at no correlation, and that can have different looks. We can have something like this where the points are kind of evenly spread right to left on the line. That would be no linear relationship. Or here we have points just sort of spread all over the place. That would be no linear relationship, or an r of 0. Or here we have a very good pattern, a smiley face pattern, but it's not linear, so the r will be 0. So that's the first step in our procedure, seeing if there is a good strong correlation, and that means we want it as close to 1 or -1 as we can get it. R equals 0, and not so good as a prediction. Step 2, we'll actually do the prediction. The full model, we use the Greek letters in here and say that the y is the intercept plus slope times x plus an error term. And that means that the points that are on this graph don't exactly line up with the line. We're fitting a line as well as we can through points. This is our line that's calculated by means of least squares. In other words, the computer is going to do all the work for you to give you a B0 and a B1, an intercept and a slope. And again, that's going to give us the line that will fit best through all of these points. So let's start with an example. And the example is going to be, is there a relationship between study time the week before a final and the score earned on the final? I've got 6 points here. So what are we going to do with this data set? Well, the first thing we're going to do is to say which is the independent variable and which is the dependent, because that's going to be important as we run our analysis. Well, think about it. What do you want to predict? Do we want to predict the study time of a person or what they're going to get on the test? Yes, it's the second. So y is going to be our dependent variable. That's going to be test score. The x is going to be the independent variable, which is study time. So in a moment, I'm going to go into an Excel spreadsheet and answer the question, what kind of a relationship do we have between those two variables? And we'll use a scatter diagram to find out. We'll find the correlation coefficient, coefficient of determination, and I'll define that in just a moment. And we'll do some prediction. We'll say, what if a person spends 9 hours studying? What will the score be? We'll also look at the practical meaning of the slope and look at a prediction for a person who spends 20 hours studying. So here's our spreadsheet of data. Notice that I've put the x variable on the left and the y variable on the right. And the reason I do that is so that everything looks okay on the scatter diagram that I'm about to do. I'll just highlight the data, put insert scatter, and there is my graph. To me, that looks like the points are going to be clustering pretty closely to a line. And if I click on the plus sign and put in a trend line, yes, the points are pretty close around the line. Looks like it's going to be a good predictor. Study time will predict final exam score. But that's all by eye. Let's see if we can do some statistics to figure out if there is a good relationship. I'll click on Data, Data Analysis, and Regression. And notice that it asks you for the y range. That's why I wanted to know up front which is the dependent variable. And that's final exam score. It also asks for the x range. I'm going to click on Labels because I did put labels in as I highlighted. And I need to specify where I want to put all of the output. So I will click on Output Range, and I will indicate that I want my information put right there. Click on OK. So here we have a lot of information all at once. And let's go over the important parts of the information on the screen. First of all, multiple R. That is our correlation coefficient. Remember, I said the closer to 1 you are, the stronger a relationship you have. So it does look like study time is very, very strongly related to final exam score. I also have something new here called R squared, and the name of that is the coefficient of determination. What is this coefficient of determination? Well, that tells you the percent of variation in y that's explained by x. And in this case, what that means is that 86% of the variation in final exam score is explained just by knowing study time. And that's pretty good. That's a lot of the variation explained. What's the other 14% due to? Well, it could be due to how much sleep you got the night before the test, whether you had crying children bothering you so you couldn't study, your previous GPA, previous experience with the material, how much you studied all the way throughout the quarter, lots of different things. But 86% predictive power, that's great. So we know again we have a very good model of prediction. Now we also have another thing here called significance. This is actually the way of telling definitively whether we have a good, strong relationship so that we can do prediction. If this figure here is less than 0.05, that means that we have a good predictive model. Let me go ahead and go back to my PowerPoint so I can show you a bit of a picture on that and tell you what this significance is. And before I go back, let me just say that this significance is pretty much another word for p-value. So let's talk about that. So you may recall from your beginning statistics class that we have something called hypothesis testing, which is a way of making decisions. We have a baseline or null hypothesis that we come in with, and the notation people use is H0. And in this case, the null hypothesis is we do not have a good predictive model. It's sort of the innocent until proven guilty in a court case, where the innocent is, no, we don't have a good predictive model. We really have to prove beyond the shadow of a doubt that it's good before we use it. Well, the shadow of a doubt is the alternative hypothesis, HA. So that would be, yes, we do have a good predictive model. That's what we will believe if we have proven it beyond the shadow of a doubt. Notice on this picture that the HA is always in the tails. So in the center of the curve is no good predictive model. If the correlation is really high, close to 1, or really low, close to -1, that's when we know the predictive model is good. So what is this p-value? What is this significance? Well, that's the chance of getting a test statistic as extreme or more extreme than the one that you found. Or in layman's terms, it's the area in the tails farther out than your correlation coefficient. So for example, if the correlation is 0.92, that's way up here, and the p-value or significance is the area farther out. I do have 3 different pictures. One is if we suspect a positive relationship, which means we put all the area for HA here. One if we suspect a negative relationship, where everything is down close to the -1. And here is if the relationship could either be positive or negative, and we don't know up front what it'll be. Big point. If the area farther out than your correlation coefficient is small, meaning less than 0.05, that means your correlation is way out in the tails and the HA holds. Bottom line, if the p-value is less than 0.05, we have a good predictive model. So back here on the spreadsheet, yes, this tells us that the overall model is good, and that's wonderful. What else is important for us on this printout? Well, something that's important is this area right here in the E column labeled coefficients. Remember that equation that I talked about with the B0 and the B1 a few moments ago? Well, the B0 is in this row. It's the 33.05. The B1, the slope, is in this row, the 5.436. And what that means is our equation is y equal 33.05, and I'm not going to type all the decimal places, I'll save myself some typing, plus 5.436. Yes, I should have put in another decimal place, I guess, if we're going to be consistent. So we've got that times x. That's my equation. So remember we said we wanted to predict for a person who spent 9 hours studying. What will that be? Well, that will be y equal 33.053 plus 5.436 times 9. That's how we find it. And now I can do this very easily by putting a click here for the 33 plus a click here for the 5.436 times 9, and voila. The score for a person who studies 9 hours is going to be 81.978 on average. And that's a good thing to know. Now, another good thing to know is, what does this 5.436 really mean? Well, that's the slope. And the meaning of a slope is, as x goes up 1 unit, what happens to y? Well, in this case, since X is hours of studying and Y is score, that says for every extra hour of studying, the score goes up by 5.436 points. So now you can do your strategic planning and say, gee, if I want to increase it from 9 hours to 10, how much will that on average increase my score? 5.436. That's important. What does the B0 mean, the intercept? Not much in practical terms. It means if you study not at all, your baseline grade is going to be 33.053. Of course, I don't think that's really too meaningful because none of you are going to study 0 hours, right? So not very practical. All right, one more thing that I'd like to talk about with this particular example is I've shown you how to do this if you happen to have a PC. But what if you happen to have a Mac? Unfortunately, you don't have data analysis. So what do you do? Well, all you need to do is to use a couple of functions which both the Mac and the PC have. The first would be the equal correl function, which I believe you're already familiar with. That's the correlation. I'll go ahead and highlight all of my study times. That's my array 1, comma, all of my final exam scores. That's array 2. And that's my correlation of 0.928. So that's good. And if I want the coefficient of determination, all I have to do is square that. So I can say equal that. I square by putting the caret and a 2, and there's my coefficient of determination. How about the intercept? Well, equal intercept. Be very careful, we need to highlight our y's. Then I can put a comma, highlight my x's, and when I hit enter, I've got my 33.05. Finally, how about my slope? Well, equal slope, very logical. Put in my y's, comma, put in my x's, and that's it. So you folks that have Macs, yes, you can do all of this just like you can with the PC. Just a little bit harder, and it doesn't give you this entire printout. Okay, I just lied. There is one more part of this problem that I'd like to look at. What if you have a person that decides to spend 20 hours studying? What would their score be? Well, that should be pretty easy, right? Equal intercept plus slope times 20. Not a problem, right? Okay, problem. What's happening is we are extrapolating outside the range of our x's, and we can't do that. In other words, if you take a look, all of the x's range between 5 hours and 12 hours. Above and beyond that, we have no idea what the trend is going to be. Above and beyond that, we really can't forecast properly. And obviously, we cannot have a test score of 141 out of 100 points. So the idea is always take a look and make sure that where you're predicting is within the range of the x's. One little caution. What if your x happens to be time, and time meaning years or whatever? What if we're forecasting the economy based on the years before? Well, we always use x's that are outside the range of the data. Is that okay? And the answer is people do it, but it's always a little bit iffy. We always put in statements about assuming that the trend stays constant, this will occur. Be careful. Well, now let's try another example, and this example is going to have some interesting little tidbits to it. So this is an example about trying to sell a used car. We want to predict what the price of that used car should be, and it's going to be based on mileage in thousands and who sells the car, whether it's an individual or a dealer. And as you'll see up here, individual is coded as a 0, dealer is coded as a 1. Also, the condition of the car, where 1 means poor condition, 2 means average, and 3 means excellent. And finally, the age and years of the car. So my question is, how can we predict price? And let's start just with one variable as a predictor, age of the car. So, first thing I would like to do is to see graphically, is there a relationship between age and price? So I will insert my scatter diagram, and there we go. And for the most part, I do see that there is a line and it's going downward, meaning as age goes up, the price is going to be dropping. Well, now that I've done that, let's see if I can do some of the analysis that I did a moment ago. I'm going to do data analysis and regression. And the question now is, what do I have as my Y range? Well, I'm trying to predict price. So my Y would be my Fs. In other words, I will pull down. I'm going to go from F1 up to F32. What is my X range? Well, if I'm only looking at age, then what I'm going to be typing in or highlighting is E1 up to E32. I do want to have my labels here. My output range, let's change that and put everything right here and click on OK. So now that I've done that, let's see if I can do an analysis, and my multiple R 0.39. Well, that's not really close to 1, so I don't think that's a really good predictor. That doesn't look good at all. And as a matter of fact, the R squared is 0.15, meaning I have 15% predictive power. 15% of the variation in price is due to age. Also, I'll move this over, and please notice the significance. That's 0.028. Wow, well that means that it is less than 0.05. It is a good predictor, but is it practically significant in addition to statistically significant? I think not. I think the 15% is really not very good. Well, what could be the problem? Because logically, I would think that age of a car would be a good predictor of price. Well, let me go ahead and just graph it one more time and point something out. I'll insert my scatter diagram, and I want you to notice this point up here, this outlier. This is a point that really shouldn't be there. Something's wrong. Could it be perhaps a specially wonderful car? Yeah. Or maybe it's a typo. So what I'd like to do is to go back now and take a look at all of my data. And the point that was a weird one was right up here. We've got a 9-year-old car with a price of $27,000. Well, okay, what if that was a typo, which it probably is? What if it was $2,700? If we can confirm that, we'll change it. And now let me run my regression one more time and see if it makes any difference at all. I am going to overwrite my existing data because I don't need the other one. That looks much, much better. Now please notice that my correlation is 0.87 and my R squared is 0.76, 76% predictive power. But now, wait a minute. According to the graph, it should be a negative relationship. The older the car, the lower the price. I'm not seeing that in this multiple R. What I am seeing, however, is that my slope is a negative number. So what's going on here? Well, what's going on is that R, the lowercase r, does range from 1 to -1, as I showed you in the PowerPoint before. Multiple R ranges from 0 to 1. Multiple R combines all the different x's that we decide to use along with our y. And so that multiple R will always be positive. That tells us that if we want to look at what the trend is, I need to look at the slope to see if it's positive or negative. And in this case, it is negative. I move this over. I do see that the significance is 1.6 e minus 10. What does that mean? Well, what that means is that I'm going to take this decimal point and move it to the left 10 places. 0.00000000016. Definitely less than 0.05. So we do have a good predictive model. And what is that predictive model? The predictive model is that the y is going to equal to 17,291.61 plus a negative, or we can just put it in as a minus, 1909.22 times x. So, what would happen if we have, say, a 5-year-old car? How much should we be willing to pay for that 5-year-old car? The answer is we should be willing to pay 17,291.61 plus this negative 1909.22 times the 5 for the 5-year-old car. The answer is we should be willing to pay $7,745.51 for the car. Further, for every year of age the car gets older, the price drops by about $1,900. So that's a very practical interpretation. Well, I know this video is getting a little bit long, but I would like to show one more thing, and that is that price is not just based on age. It could be based on all of these other variables. So how am I going to deal with that? Well, what I'm going to do is multiple regression, which is basically just a lot more of what we've done. Unfortunately, Excel on the Mac cannot do it, so there are some other programs out there that can do it, or else get yourself a PC. Just borrow a PC to run it. But let me go ahead and demonstrate this. I'm going to use mileage in thousands as an X, who sells it, which is a dummy variable, a 0, 1, a qualitative variable. That could be a predictor of price. Age, like I did before, but also condition of the car, whether it's in poor, average, or excellent condition. Unfortunately, however, I need to do something with this before I can use condition as a variable. The reason is the 1, 2, and 3 is not a quantitative variable where I can talk about the difference between a 1 and a 2 being the same as difference between a 2 and a 3. Rather, I'm going to need to develop 2 new variables for condition, 2 new dummy variables. And let's see how I'm going to do that. The first thing I'm going to do is to insert a couple of variables. So I will insert, and now I have 2 new columns to put in some 2 new variables. And one of the variables is going to be called poor, and the other variable is going to be called average. I've just taken the lower levels of condition to name those. Next thing is I'm going to have to figure out what values the poor and the average are going to need. And the easiest way of doing that is if I go ahead and sort my data. So I'm going to highlight my data. I'm going to do a data sort. And I'm going to sort by condition from smallest to largest. So now my life's going to be a little bit easier. So this first case, car number 2, I said that that was a condition 1, which is poor. I'm going to put in a 1 for poor, meaning it is a poor condition car, and a 0 for average, meaning it's not average. I will then go ahead and highlight that. Oh yes, the computer is giving me trouble. Highlight that and pull this down. Now how about for a condition 2, an average condition car? Well, it's not poor, it is average. So now I can go ahead and drag that down for all of those cases. How about the 3s, the excellent condition cars? Well, it's not poor, it's not average. So I will have 0, 0 for all of those cases. And now that I've created all of those, what I'll do is simply delete condition. I don't need that variable any longer. Okay, let's get back into our regression procedure. Data, data analysis, and regression. My input Y range is no longer my F column. Rather, now it's my G column. So I'm going to put in G1 up to G32. My input X range is everything from the B through F column, so I will put in B1 through F32. I've got my labels in there, and now what I'm going to do is to just simply say, put the answer in a new workbook, and I'll click on OK. Okay, so here are my statistics, and let's take a look at what we've got. The multiple R is now 0.93. That's important. That again is on a scale from 0 to 1, and it's definitely close to 1. So I know I've got a good predictive model. My R squared, 0.86, 86% predictive power. Well, that's about the same as what we had before. What can I say? I don't know whether we've improved things any based on this new model. Well, my significance is a little bit smaller, definitely still less than 0.05, so that means that I've improved something. But now, which are the good variables of all of these that helped us to predict the price of the car? Well, all I need to do is to look at my p-values here and realize that any of the p-values for my independent variables that are less than 0.05 are good predictive variables. What's less than 0.05? Age. And that's it. That's why my R squared hasn't really improved from the last time I ran it alone. We do see that we've got the rest of the variables in here, positive and negative. I could theoretically use my entire model, although I'm not sure that it really warrants using. My philosophy is create regression models with the best predictive power using the least amount of variables at once. But folks, if you really wanted to use the full model, let me show you what that would look like. It would be y equal 16741.84. That's my intercept, plus a negative 30.9696, and that's times mileage in thousands, plus 1296.967 times who sells it, whether it's the individual or the dealer, minus, or we could put it in as a plus, the negative 1862.76, and that's going to be times poor, my new variable, plus the negative 873.815 times average, and then finally we get to the thing that's actually good, my negative 1312.07 times age. So now if I had, say, a car that has 20,000 miles on it, sold by the dealer in poor condition, and it's 9 years old, I could go ahead and plug those values into that equation and have my prediction. Again, would I actually do that in real life? Probably not. Probably what I would prefer to do is to go back, get rid of that one, and use the variables here that are a little bit better. Yes, my prediction that I just did is a little better than the 76% predictive power, but not really that much. Well, hopefully this has helped you understand a little bit more about regression. Sorry it went on so long, but hopefully it was helpful. Take care.